Hi children, welcome. Welcome to another chemistry class. In this session, we are discussing another important chapter. It is Unit 8 of second year topic, D and F block elements, transition elements and inner transition elements. That is what the point of discussion in the chapter. Okay, so let us go through the important aspects of transition and inner transition elements, right? D and F block elements. This is the NCERT content from the concerned chapter. D block elements. First of all, it is D block elements. D block elements. It is group 3 to 12. All of you know. Group 3 to 12. Where d orbital filling occurs. Where d orbitals filling occurs, d orbitals are progressively filled in each of 4 long periods. 4 long periods, right? 4 series of elements. Of course, a detailed discussion is only about 3 series. First transition series, which is called 3D series, second transition series called 4D series, and third transition series called 5D series, right? The 6D series, that is the fourth one, it is all artificial elements. We don't discuss much of the chemistry concerned. So 3 series are important, particularly first series we are going to discuss in detail. Meanwhile, F block elements, we have 2 series, 4F series and 5F series. All of you know, 4F series called lanthanoids, coming as a continuation of lanthanoids, and 5F series coming as a continuation of actinoid, and that is actinoids, actinium continuation, where the orbital F orbitals are filled. They are put separate panel at the bottom of the periodic table. We call them transition metals and inner transition metals. D block elements are called transition metals and F block elements are called inner transition metals. All of you know regarding the electronic configuration of transition and inner transition elements. For transition elements, that is D block elements, the electronic configuration is a noble gas core, N-1 D 1 to 10 Ns 1 to 2. This is the electronic configuration for D block elements. A noble gas core, N-1 D 1 to 10 Ns 1 to 2. It can be sometimes Ns 0 to 2 also, because Ns 0, there is one configuration, palladium. Palladium stand with the configuration Ns 0, like that. So this is the electronic configuration for D block elements, and electronic filling occurs over here. N is valence shell. N is valence shell and N-1 is penultimate shell. N-1 is penultimate shell. So the electrons are entering over here. Electrons are entering in D orbital of penultimate shell. Usually S and P block elements, when we discuss, the electrons entering in S orbital of valence shell, S block. The electron entering, last electron entering in P orbital of valence shell, P block. While coming to D block elements, the last electron, differentiating electron, enter into D orbital of penultimate shell, N-1 D. And how that filling occurs, all of you know, D orbital, there are 5 orbitals, and the filling will be occurring in such a way that D1, 1 unpaired electron, D2, 2 unpaired electron, D3, D4, D5, 5 unpaired electron, D6, 4 unpaired electron. So number of unpaired electron increases from D1 to D5 and then decreases. D6, D7. D7, 3 unpaired electron. D8, 2 unpaired electron. D9, 1 unpaired electron. And D10, 0 unpaired electron. Like that. So 1 to 10. D orbital filling, all of you know, it is 1 to 10. Obviously, there are 10 groups in the block. 10 groups, 10 elements in a series. That is what group 3 to 12. Group 3 to 12, 10 groups are present because D orbital filling occurs. Meanwhile, if you go to inner transition element, there will be F orbital filling and electronic configuration of F block. It is going to be a noble gas core once again. N-2, F1 to 14, N-1, D0 or 1, Ns2. This is the electronic configuration for F block. How do you understand? This is the valence shell N orbit and this is N-1 penultimate shell, right? And electron filling occurs in pre-penultimate shell. Electron filling occurs here. This is called the pre-penultimate or anti-penultimate. Pre-penultimate or anti-penultimate F orbital 1 to 14. As all of you know, in F there are 7 orbitals. In F there are 7 orbitals. There are 7 orbitals, 1, 2, 3, 4, 5, 6, 7 orbitals. And electronic filling will be F1, F2, F3, F4, F5, F6, F7, F8. So up to 7, the number of unpaired electron increases and 8th electron pairing starts and then the number of unpaired electron decreases like this. So there will be 14 electron filled in F orbitals and that is called F block elements, and there are 2 series as all of you know, 4F series called lanthanoids, 5F series called actinoids, right? There in a series there will be 14 elements, while transition elements in a series only 10 elements, right? There are mainly 4 series of transition elements. First one called 3D series, scandium to zinc. 4D series, yttrium to cadmium. 5D series, lanthanum. After lanthanum, 14 elements, cerium to lutetium, that is lanthanoids. And after that, hafnium to mercury continuous. 6D series, after actinium, what do you call, thorium to lawrencium, 14 elements, that is called actinoids. After that, it is continuing 2 series of inner transition elements, 4F, cerium to lutetium, lanthanoids, and 5F, thorium to lawrencium, called actinoids, right? Let us go through the elements in detail. If you go through the periodic table, it is quite simple to understand. You see, this is the first transition series starting from atomic number 21, calcium 20, 21 to 30. That is the first transition series, all of you know. It is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. 21 to 30 continuous. 21 to 30 continuous. Once again, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. While the second series, starting from after strontium 39 up to 48 continuous. Yttrium, zirconium, niobium, molybdenum. Technetium is an artificial member. All these elements are artificial. All these elements are artificial. Promethium is artificial. Technetium, first artificial element. In fact, the name technetium stands artificial. So yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, up to 48. So all continuous elements. Meanwhile, you can see after 56 barium, 57 lanthanum, it is put separately. 14 elements put separately as a continuous from lanthanoid. Lanthanum, lanthanoid. Cerium to lutetium. 58 cerium to 71 lutetium. Only after that it is continuing here. Hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, silver, mercury. Mercury is the liquid metal, all of you know. Mercury is the liquid metal. So once again, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, lanthanum, 14 elements. After that, hafnium, tantalum, tungsten. Tungsten, all of you know, highest melting metal is tungsten. Melting point is very high. In fact, resistance is very high. High resistance, tungsten. Then rhenium, osmium. Osmium is the densest element in the periodic table. Osmium. Of course, with a tight competitor, iridium, also densest. Platinum, gold, mercury. It's quite surprising or quite interesting to see that high melting tungsten and low melting mercury in the same line. Right? These are the three important series we are going to discuss, particularly first series. A detailed chemistry is dealt about the first series. Of course, the others are also coming into the discussion. Originally, the name transition metal derived from the fact that their chemical properties, transition. What is the meaning transition? Chemical properties between those of S and P block elements. Transition means deviation. The name is so given. Transition metal. The chemical properties between S and P block elements. That's how the transition name given. But now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in the neutral atom or in their ions. So what is a transition metal according to IUPAC definition? Either in the neutral state or in the ion, means in the compound form, they should have unpaired electrons, incomplete electron in d orbital. In fact, the three elements zinc, cadmium, mercury, they are out of the definition of transition elements. You see that zinc, cadmium and mercury, that is group 12, have full D10 configuration in their ground state as well as in their common oxidation state, and hence they are not regarded as transition metals. They are out of the definition of transition metals. Who all? The last members, zinc, cadmium, mercury. Zinc, cadmium, mercury. They are out of the definition of transition elements. Group 12, zinc, cadmium, mercury. They have 3D10, 4D10, 5D10 configuration in the ground state, elementary state, as well as in their any compounds. So they are actually out of the definition of transition elements. However, being the end members, they are put along with the transition metals, we put along with the D block elements. Various precious metals various precious metals, all of you know, silver, gold, platinum, fall under transition elements. Industrially important metals, iron, copper, titanium, industrially important metals falls under this category. First row series, we call it as 3D transition series. First series, which are the first series? Atomic number 21 scandium to atomic number 30 zinc. Which are all the elements? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Exactly. And it's quite interesting to see their arrangement, electronic configuration and their group. That's quite interesting to see their group and electronic configuration. It is group number 3. We have scandium, atomic number 21. Atomic number 21. The configuration is 3D1 4s2. You can very well see this digit atomic number will reflect in the electronic configuration. 21, no? 3D1 4s2. Number 1 point. Number 2 point, the sum of these digits will be group number. You go to next, group 4, scandium, titanium. Titanium atomic number 22. What is the electronic configuration? It is 3D2 4s2. And now 2 plus 2, group number 4. And group number 5, scandium, titanium, vanadium. That is atomic number 23. 23. It will be 3D3 4s2. And 2 plus 3, group number 5. Right? And group number 6, scandium, titanium, vanadium, all of you know chromium. Chromium has got a exemptional configuration. All of you may be remembering, even learning from the lower classes itself. Chromium expected to be 3D4 4s2, but actually it is 3D5 4s1. Maybe due to extra stability of half-filled configuration, chromium having 3D5 configuration, we know that. Now, group number 7, after chromium, it is manganese, atomic number 25. As expected, it is 3D5 4s2. 3D5 4s2. Then, atomic number 8, it is chromium, manganese, scandium, titanium, vanadium, chromium, manganese, iron. Atomic number, how much? 25, 26. It is 26. It is 3D6 4s2. All these you can find. You see this? 3D5 4s2. 2 plus 5 7. 3D6 4s2. 2 plus 6 8. So the electronic configuration reflected in the digit of atomic. If you memorize the atomic number, you can find which group it is, which can find which what electronic configuration it has got. After iron, it is group number 9. It is iron, cobalt, atomic number 27. It will be 3D7 4s2. 3D7 4s2. 2 plus 7 9. Now 10th group, it is nickel, atomic number 28. What will be? 3D8 4s2. 3D8 4s2. 8 plus 2 10. And now atomic number 11, copper, group number 11, atomic number 29. It is 3D9 4s2. 2 plus 9 11. And group number 12, zinc, atomic number 30. It will be close filled configuration. 3D9 becomes 3D10 4s2. Hello, there is one configuration exemption. Exemption in chromium and exemption in copper. This we have written 3D9 4s2. All of you know it is wrong. What is correct? What is correct? There is exemptional configuration in chromium as well as copper. What is the configuration of copper? We are expecting 3D9 4s2. Actually, it is 3D10 4s1. There are two exceptional cases in that first series, chromium and copper. In fact, D and F block elements are full of exceptions. There are lot of elements which are actually giving a different configuration than what we expect based on Aufbau principle. As I said earlier, palladium. Different elements are giving variety of oxidations, variety of variations in their electronic configuration just because of the fact, not only in D block, F block also, just because of the fact that these orbitals, they have only slight difference in their energy. If you go to 3D 4F, 3D 4S, the energy difference between 3D orbital, 4S orbitals are marginal. So quite often we can expect there are variations in electronic configuration against what we learn according to Aufbau principle, the rules and regulations. Many times they violate from rules and regulations. Even you can say they are called transition elements because they violate, they do transit. Transition is shown. So 3D10 4s2. This is the first series of elements which are very important. And if a question comes, how many unpaired electrons in iron, you must be able to say iron, how many unpaired electron? It is 3d6 4s2. Anyway, this is paired electron system. How much in 3d6? It will be 1 2 3 4 5 6. There are 4 unpaired electron. There are 4 unpaired electron. Like that, we are able to give a reply which is based on their electronic configuration, and that electronic configuration you can memorize with their atomic number and the order. Regular order, atomic number 21 to 30. Atomic number 21 to 30, a regular order. Is that perfect? So that is about the transition elements and their, this is what, this all things we did. Electronic configuration we did. Exceptional configurations we had a talk on. And this is what just now we have gone through. The first transition series. Scandium to zinc. Scandium to zinc. And the electronic configuration also we have seen. Let us go through second series. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. You can see D1S2, D2S2. There is no D3S2. You see D1S2, D2S2. No D3S2, D4S1. D5S1, okay, half-filled stability. D6S1, 7S1, 8S1, 10-0, palladium, 10-0. Quite frequently, you can find exceptional configurations because of very small difference in their energies. Coming to the next, lanthanum, after 57 lanthanum, 58 cerium to 71 lutetium, lanthanoids. After that, 72 hafnium. You can see the configuration. D1S2, D2S2, D3S2, D4S2, D5S2, D6S2, 7S2. Here only one difference. It is not 8S2, 9-1, 10-1, 10-2. Two cases there is an exceptional configuration in the third series. While fourth series, I am not, we don't have to go through that. Anyway, it's given there. You can just go through, they are all artificially transmuted elements. Okay. Electronic configuration of zinc, cadmium, mercury, and their point is commented there. Dn configuration and their magnetic property, magnetic and electronic property, I have already commented. And regarding transition metals, this is one very important point. I think all of you will agree. They show variety of oxidation state. Transition metals are known for performing variety of oxidation state. Formation of colored ions. In fact, transition metal compounds are adding color to chemistry. Colored ions, then entering into complex formation with a variety of ligands. In fact, coordination chemistry greatly contributed by transition elements. They exhibit catalytic property. Transition metals and compounds exhibit catalytic property. Paramagnetic behavior. In fact, many metals are ferromagnetic. Permanent magnets are prepared by many of the related alloys. See, there is more horizontal similarity than vertical. In fact, here we discuss in terms of horizontal similarity as periods. Series of first series, second series. Of course, there are few vertical similarities. Most of the similarity we discuss horizontal similarity. Of course, a very few vertical similarity also. That is about physical properties. Typically, they show high tensile strength, ductility, malleability. The typical metallic characters are given by the heavy metals transition elements. And exceptional cases will be zinc, cadmium, mercury, manganese. Particularly zinc, cadmium, mercury, they are called volatile metals. In fact, manganese also somewhat volatile. Zinc, cadmium, mercury, volatile metals. Manganese also somewhat volatile. You may go through this table to get a fair idea regarding most of the popular elements, how their crystalline structures are available. For example, if you take up these part, you can find these two groups, mainly HCP. Coming to these 2-3 group, mainly BCC. Here also BCC, HCP, all here it is CCP. Like that, you can get a fair picture regarding how their crystal systems are coming, particularly most popularly known elements like say iron, BCC, HCP, copper, CCP, zinc, typical metallic structure with somewhat HCP, like that. Platinum, CCP, gold, CCP, silver, CCP, palladium, CCP. So most commonly encountered popular elements, how their crystalline structures are coming, you can get a fair picture regarding their crystalline arrangement from the table, right? On to the discussion on melting point. Melting point, we can go through a discussion, the trend, how the trend comes in the melting point of transition metals. That is in the NCERT diagram figure 8.1. See, it's quite simple to understand. The three series of elements, their melting point is given. A general trend is the melting point increases and comes to a maximum and then decreases. So as you move from left to right in the series, the melting point increases. What is the reason for increase in melting point? Quite naturally, the metal-metal bonding increases due to increase in the number of unpaired electron. As the number of unpaired electron increases from left to mid, we can find the metal-metal bonding increases, which causes increase in metallic bonding, increase in melting point, right? But of course, there are few exemptions we can find. You see the element manganese. Manganese having high number of unpaired electron. It is D5 system, but it is seen to be volatile. So those electrons may not be contributing good towards the metal-metal bonding. Similarly, somewhat a minimum, less character in technetium also, but we don't find that in the third series. The 5D series, we don't find that abnormality. Tungsten, all of you know, the maximum melting element is tungsten. Among the transition metals, or in fact in the metals, the highest melting metal is tungsten, W, wolframs, right? So that is the general trend. When we move from left to mid, as the number of unpaired electron increases, the metallic bonding character increases and the melting point increases, reaches to a maximum, and then decreases as the pairing starts. Number of unpaired electron increases from 1 to 5 and then decreases from 5 onwards. It is as the pairing starts, right? The exemptions are manganese, technetium. Manganese in fact is a volatile metal somewhat. And of course you can find zinc, cadmium, mercury, which are volatile metals. Zinc, cadmium, mercury, which are volatile metals, and their range of melting point is not coming in this range and is not shown in the diagram. Okay, so that is regarding the melting point of transition metals. A similar diagram you can encounter for the enthalpy of atomization, because enthalpy atomization diagram, melting point diagram will be quite similar. Why it is quite similar? They are direct functions, you can say, right? Metal-metal bonding is reflecting in the enthalpy of atomization, otherwise called enthalpy of sublimation. So greater the metal-metal bonding, greater will be the enthalpy of atomization, greater will be the melting point. So you see metal-metal bonding is increasing from left to mid and then decreases, right? And you can find some interesting points also. You see this particular sentence, each and every point in NCERT is important. You see, another generalization that may be drawn from figure 8.2 is that metals of second and third transition series have greater enthalpies of atomization than the corresponding metals in the first series. This is the first series, this is second series, and this is third series. Second and third series having greater enthalpy of atomization compared to first series. What is the reason? This is an important factor accounting for occurrence of much more frequent metal-metal bonding. So whether it is dealing with the enthalpy of atomization or dealing with the enthalpy of melting point value, it is closely related to metallic bonding character. Greater metallic bonding, metal-metal bonding observed in heavy members. Which heavy members? Not the first series, second, third series. That is 4D, 5D series, right? So that is about melting point and a comparative study on the enthalpy of atomization, right? Now it is a talk on atomic size. Now it is a talk on atomic size. Look at the atomic size coming. Atomic size, you can see in each series as you move from left to right, atomic size gradually decreases. Atomic size is gradually decreasing as the electrons are added to d orbital. You know, d orbitals are not good enough for the shielding purpose. So as you move from left to right, as the electrons are being added to d orbitals, you can see the size gradually decreases, and once you reach at the end portion, as the filling is occurring, the size is slightly increasing. A slight expansion in the atomic size is also observed. But that is not a quite interesting and important point to be noted here. The point to be noted is, look at the graph. This is the first transition series. This is first transition series. This one. And this is second transition series, and this is third transition series. First transition series, 3D series from scandium to zinc, that is lying somewhere here, you see. And the second transition series, that is 4D series, yttrium to cadmium, it is upper. Quite naturally, as you come down, the size should increase. So first series, second series size is larger than the first series. Quite natural. We know down the group size should increase, no doubt. Now, what about 4D, 5D? What about the second series and the third series, 5D series? Here there is a considerable decrease in the difference in the size, while here the difference is very small. Don't you see the difference is very small? Not even very small. Many cases the values are either the same or slightly differing by 1 unit, greater or lower. So 3D, 4D series, there is a significant or considerable difference in the atomic size increases. But 4D, 5D, there is no much difference. What is the reason? The reason is the reason is attributed to, all of you know, after Lanthanum. I am talking about 5D series. After Lanthanum, what is happening? After Lanthanum, what is happening? There are 14 elements being already we have discussed about this. After Lanthanam, you see this is first series 3D series, 4D series, and this is 5D series. Lanthanam, cerium to lutetium, electron orbitals, elements are, the electronic configuration happens in F orbital. You see that? Lanthanam, after Lanthanam, cerium to lutetium, they are F block elements and electrons are filled in F orbital. And we know F orbitals are poor screening effect. Due to poor screening effect, the effect of nuclear charge increases. Nuclear attraction increases. And there will be a gradual decrease. As you move from cerium to lutetium, there will be a gradual decrease in atomic size. And after that decrease, we come here with the hafnium. So hafnium comes as a continuation of cerium to lutetium. After 71 lutetium, 72 hafnium is coming. So whatever contraction happened here is very popular one, all of you know, lanthanoid contraction. So after lanthanum, we come to hafnium. Before lanthanum, hafnium, 14 elements experiencing contraction. And that contraction is called a lanthanoid contraction. Why there is a contraction? Due to increase in nuclear, effective nuclear charge. Why there is an increased effective nuclear charge? Why there is an effective increase in nuclear attraction? Due to poor shielding effect of F orbitals, and of course D and F orbitals are giving poor shielding effect. Here F orbital configuration is preceded. Quite naturally the size decreases. After that size decrease, once you reach here, the size will be lower. So here to here there is a good difference, reasonable difference in the size. Compared to this and this is larger. But compared to this and this, such great size we don't observe. Rather, in fact, it is a lower size. That is what we are experiencing over here. You can see first series, second series, there is a good difference. But second and third series, the difference rather is very low. Hope you understand. It is a consequence of the very popular phenomenon, lanthanoid contraction. So due to lanthanoid contraction, 3D series, 4D series, there is a good difference in the atomic size. But 4D, 5D series of elements, they are very close to each other due to lanthanoid contraction. This is an important consequence of lanthanoid contraction also. Right? That's about size. Now, what other properties? Now, there is a talk on electronic configuration and some important properties which you can see. Electronic configuration and some important properties of 3D series elements. 3D series elements. You can see the electronic configuration of starting from scandium to zinc. You can see D1S2, D2S2, D3S2, D5S1. Over chromium, there is a difference in the electronic configuration. Already discussed. Then D5S2, D6, D7, D8, D9S2, it is D10S2. So chromium, copper. There is a difference in the electronic configuration. It's a well-known fact. What about the unipositive ion? Unipositive ion, electron are usually removed from S orbitals, it is D1S1, D2S1, D3S1, like that it goes. Dipositive ion, electronic configuration of dipositive ion, I think that is moving regularly. D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. It's a regular configuration, dipositive ion. And tripositive ion, this is noble gas system. Scandium tripositive ion will be noble gas system. And tripositive for copper, zinc is not available. They don't give tripositive ion, they give monopositive or univalent or divalent character only. Okay. Now, enthalpy of atomization, which got a low value or which got a high value, that is a kind of comparison you need to do from the tabulated information. You need to go through meticulously regarding how the data is, not to by heart the data. not to by heart the data. In fact, you need to have a precise idea regarding which is minimum, which is maximum, or some order is given. If there is some exceptional features of ordering, that you need to know. Which is minimum? Which is minimum? I think zinc is minimum. Zinc, the most volatile metal. The most volatile metal, I told you, zinc, cadmium, mercury are volatile metals. That is minimum. Zinc is minimum. Which is coming next after zinc, you see another volatile metal, manganese. After zinc, it is manganese. And then after manganese, which one comes? I think it is scandium, the lightest metal, scandium. So zinc, manganese, scandium. I think I am making the correct order. 326, and there is 339 copper coming. Then which one? 397 chromium coming, which is maximum. Which is maximum atomization enthalpy. In fact, greater the atomization enthalpy means relatively the metal can act as a noble, right? So which is maximum? Maximum, I think it is for vanadium. For vanadium, the value is maximum. So we need to have such a idea which has got a minimum value, which has got a second value, which has got a maximum value. Is there any abnormal data like that? Okay. Next is ionization enthalpy. You can see 3 ionization enthalpy values are given, which got a minimum first ionization enthalpy. Minimum first ionization enthalpy. I think it is scandium. Minimum value 631. Please verify, isn't it 631 minimum? And which is maximum? Maximum, it is zinc. So first ionization enthalpy, minimum scandium, maximum zinc, right? Minimum scandium, which is coming second 650. I think it is 650 vanadium second place, which is second from the maximum. 906 is there, and there is 762. I think this is maximum. Iron, the first ionization enthalpy, second place. So it can be referral questions based on, not based on the data, but based on the relative order. There can be a question. What about second ionization enthalpy? Second ionization enthalpy, minimum value. I think it is once again minimum scandium. Scandium, second ionization enthalpy, minimum. What about the maximum value? Maximum value, I think there is a surprise. It is not the zinc. In fact, it is copper. The second ionization enthalpy value, maximum, it is not the zinc. It is copper, right? So that is quite interesting to see, because you see second ionization enthalpy, copper is getting D10 configuration. So removing one more electron from D10 will be tough, no? So the value is increasing. So you can relate these values with the electronic configuration, and how that electronic configuration versus the ionization enthalpy values can be correlated, and may not be used successful in all the cases, because there can be very exceptional different scenarios, but mostly you will get a picture and you will get a link how to connect the value differences versus electronic configuration, because ionization enthalpy closely related to electronic configuration also. So minimum value scandium, maximum value it is not zinc, in fact it is copper. And after copper, I think it is not even zinc. Then also it is nickel 1752, and after that only zinc is coming. Now what about the third ionization enthalpy? Third ionization enthalpy, once again I think first, second, third all minimum for scandium. First, second, third all minimum for scandium, because scandium will be bigger in size. Bigger the size of the atom, lower will be the ionization enthalpy. No doubt about it. So whether it is first ionization enthalpy or second ionization enthalpy or third ionization enthalpy, minimum is for scandium. That's a quite interesting observation. While maximum for third ionization enthalpy, I think it is zinc again. Zinc is having maximum third ionization enthalpy. In fact, ionizing third position is not possible for zinc. You see, third ionization is not possible for zinc as it is having 3d10 4s2. Only that s2 electron can be removed. Removing third electron will be a quite tough job. You see that value 3837. 3837. In fact, the relative stability of the oxidation state you can compare with the sum of ionization enthalpy values. Lower the sum of ionization enthalpy values, greater will be the stability of that particular ion. Okay. So there comes. Can you just try to visualize the third value for manganese will be pretty high than what we expect. Third value for manganese, you see, third value for manganese, it is pretty high than what we expect. You see, it is 3260 compared to the nearby value, it is very high because third electron removal is tough because you have 3d5 system. Removing electron from 3d5 will be requiring more energy, right? What about chromium? Chromium second ionization. Chromium second ionization will be slightly greater value. Chromium second ionization will be slightly greater value because it is again having D5 configuration. So D0 configuration will be stable due to noble gas system. D5 configuration will be extra stable, right? Due to there are a lot of concepts. One important concept we are dealing in the NCERT is exchange energy, maximum possibility of exchanges. Therefore, D5 is extra stable, D10 is extra stable. So, half filled and fully filled configuration stability, that is an important point. Now coming to similarly metallic ionic size, you can see it will decrease this way and then slightly increase. As I already told you, the metallic size is decreasing all the way as the electron getting filled in d orbital, and at the end of it, when the filling is completing, the size gradually increases. And this is one of the most important point of discussion regarding standard electrode potential. Standard electrode potential value M2 plus bar M. I think all of you know regarding what is the importance of that value. For example, high negative value performed by this. High negative value performed by scandium titanium. What does that mean? What does that mean? All of you know. E0 value, isn't it titanium? Scandium titanium. E0 value Ti2 plus bar Ti. It is minus 1.63. What is the meaning? Is it means like this reaction is feasible or this reaction is feasible? What is the meaning? All of you know, but still I am asking, right? Suppose a high negative value. What is the meaning? Is this reaction comfortable or this reaction comfortable? Exactly. This reaction is comfortable. Rather, this reaction is less feasible. So we can say this is easily oxidized to this, and this acts as a strong reducing agent. So a high negative value seems like the species in the reduced form. It's a good reducing agent. This will be a good reducing agent as it undergo easy oxidation, right? What about if the value is high positive? For example, here we can see 1.97 plus M3 plus bar M2 plus. Which species it is? Iron, cobalt, nickel, copper, zinc. It's cobalt, it seems, right? So E0 value for CO3 plus bar CO2 plus 1.97. What does that mean? Once again, is it like this is happening easily or is it like this is happening easily? A high positive figure indicates this is happening easily. That means this undergo reduction easily and this is a good oxidizing agent, like that. So determining the character whether oxidizing or reducing can be determined by standard reduction potentials, and you can see almost all species second ionized state M2 plus bar M value, the standard reduction potentials, all species are having negative values. All species having negative values except copper. Except copper. except copper alone having a positive value plus 0.34. That is the value standard potential. So copper seems to be a bit oxidizing in nature, while others are basically reducing in nature. Okay, and even that is there in the electrochemical series. In the electrochemical series, copper coming above hydrogen, while all others will come below hydrogen, right? So that in fact is a very important point. Which is the densest element in the series? Which is the densest element in the series? In fact, this is the lightest element. Scandium is the lightest transition element. Scandium is the lightest transition element. Which is the heaviest one? Heaviest one. Heaviest one, it seems these two. These two are the heaviest one. Heaviest transition element. Second lightest, this is second lightest, and then gradually it increases. In fact, zinc is less dense than the regular series, right? So lightest metal will be scandium, heaviest is observed copper, nickel, almost coming equal values. That's about the atomic and physical properties of 3D series. I told you there are three important series. A detailed discussion happens on 3D series. Okay. Now, what is the next point of discussion? Ionization enthalpies. Already we had a detailed talk on ionization enthalpy. Next is an important point regarding oxidation state. Oxidation state of transition metals. Transition metals are well known for performing their variable oxidation state. All of you know they are well known. That's a typical characteristics of transition elements. Transition elements are well known for their variable oxidation state, well known for their colored compounds, well known for their paramagnetic behavior, catalytic activity. These are all important characteristics of transition metals, and of which the most important one is their oxidation state. Look at the variability in oxidation state. Scandium, only one state is shown, plus 3 state. Titanium, plus 2, plus 3, plus 4. Vanadium, 2, 3, 4, 5. Chromium, 2, 3, 4, 5, 6. And the most commonly observed oxidation states are shown with the bold letters. So as you can see, scandium to manganese, the variability in oxidation state increases. So variability in oxidation state increases from scandium to manganese and then decreases. So maximum number of oxidation state performed is by manganese. No doubt why it is, because it is having 3d5 4s2, 3d5 4s2, maximum number of electrons that can take part in chemical bonding. It is 3d5 4s2, all 5 electrons from d orbital and 2 electrons from s orbital. If they take part in chemical bonding, the maximum it will be plus 7 state. And beyond manganese, pairing starts. As the pairing starts, again the chances of contributing towards the oxidation state will decrease, no, as all of you know, right? So you see, 1 state here, 3 state here, 4 state here, 5 state here, and here it is 6 state, 2, 3, 4, 5, 6, and it is quite reasonable and interesting to see. Unlike the variability in P block elements show variable oxidation state, but their variability differ by a unit of 2. Suppose we are talking about chlorine, the variability in oxidation state 1, 3, 5, 7, it differ by 2 units. While here the oxidation number differ by 1 unit. You see that 2, 3, 4, 5, 6, 7 continuous. That is what the nature. Iron 2, 3, 4, 6, cobalt 2, 3, 4, nickel 2, 3, 4, copper plus 1, plus 2, zinc only plus 2. So scandium and zinc show only one oxidation state. Not quite surprisingly, scandium, yttrium, lanthanum, they are called non-typical transition elements. Many of the properties shown by transition elements are not observed for those elements. They are called non-typical transition elements. So that is about the oxidation states of elements. It is increasing. The variability increases towards mid and then decreases. Okay. You see the important point which I have commented just now. That's a very important point which I have commented just now. The variability of oxidation state, a characteristic of transition elements, arises out of incomplete filling of d orbital in such a way that their oxidation state differ from each other by unity. Vanadium 2, vanadium 3, vanadium 4, vanadium 5. This is in contrast with the variability of oxidation state of non-transition elements, where oxidation state normally differ by unit of 2. So non-transition elements, that is representative elements, that is in the p block elements. In p block elements, there can be variability which differ by 2 units. Here, the variability differ by 1 unit. And there is yet another important point. What is the important point? You see, in P block, the lower oxidation state are favored by heavier members. You know, inert pair effect. If you take group 13, +3 state is dominated by boron, aluminium, etc. But as you come down, heavy member thallium interested to show +1 state. If you go to group 14, carbon silicon favorable to give +4 state. But as you come down, heavy member lead, it is showing +2 state. So that is what called the inert pair effect. All of you know. Group 13, 14, 15, 16, etc. As you come down, heavy members prefer to give a lower oxidation state, 2 units less than the group oxidation state, called the inert pair effect. Which basically due to, all of you know, which is basically due to the inertness, the reluctance shown by the 6s2 electron in those atoms. Because they are under more control of the nucleus. They don't want to take part in chemical bonding. For example, lead 6s2, 6p2, that is the ending configuration. That 6s2 electron act as a inert pair. They don't want to take part in chemical bonding. Why? They are more under the control of the nucleus due to imperfect shielding provided by the d and f orbital electrons which are coming intervening, because they are heavy members. Now, due to inert pair effect in p block, for heavy members, lower oxidation state is more stable, while here it is not like that. Here it is not like that. The opposite is true. The opposite is true in group D block. For example, group 6, molybdenum 6, tungsten 6 are found to be more stable than chromium 6. The elements are coming like this. Group 6, the elements are coming like this. Chromium, molybdenum, tungsten. Chromium +6 is stable. Chromium +6 is forming. Molybdenum +6 forms, tungsten +6 forms. For tungsten molybdenum, +6 state is more stable than chromium. It is not this way in the main group element. In main group element, for heavy members, lower oxidation state is stable. But here, if you take as an example, molybdenum, chromium, molybdenum, tungsten, the heavy members, molybdenum, tungsten, they are stable at a higher oxidation state. Do we have any evidence? Definitely we have evidence. What evidence? Look at the evidence. Thus, chromium 6 in the form of dichromate in acid medium is a strong oxidizing agent. Chromium 6 will be easily converted to chromium 3. As all of you know, Cr2O7 2- chromium 6 easily converted to 2Cr3 plus in acid medium. It's a very good oxidizing agent. So chromium in the +6 state easily converted to +3 state, undergo reduction, act as good oxidizing agent, while molybdenum +6 state is not a good oxidizing agent. MoO3, where molybdenum is +6 state, it is not a good oxidizing agent. It doesn't want to go to +3 state. Tungsten oxide, WO3, it is not a good oxidizing agent. Rather, it doesn't want to, why? Because it doesn't want to go to +3 state. Because +6 state is found to be stable for heavy members. That is a contradictory observation from P block elements. A very important point. Meanwhile, lower oxidation states are also found in complexes. Low oxidation states are found when complex compounds ligands capable of pi acceptor ligands. We are talking about pi acceptor ligands, back bonding, synergic bonding, etc. in another chapter, that is coordination chemistry. We can discuss in detail. If you take nickel tetracarbonyl, nickel is 0 oxidation state. Iron pentacarbonyl, iron is 0 oxidation state. So metal carbonyls, metal found to be 0 oxidation state. So in complexes like metal carbonyls, where carbon monoxide act as a pi acceptor ligands, it is capable of accepting pi electron density through back bonding from the metal ions. That is what called a pi acceptor ligands, pi acid ligands. In such cases, their oxidation state, metal oxidation state found to be 0. That's an important observation. So various points which we have discussed within these minutes, it was basically various, the series of elements and their order. First transition series, second transition series, third transition series, its order of arrangement. How the order related with the inner transition elements, electronic configuration, etc. Their metallic structural features, melting point graph and related points. Then enthalpy of atomization, a detailed talk on electronic configuration, ionization enthalpy, enthalpy of atomization with reference to the tabulated data, right? And then what? Standard reduction potential and its characters, right? Oxidation state, very important one, oxidation state, right? Yes. Now, a talk on the standard reduction potential with the graph, standard reduction potential with the graph. You see the graph once again. The data already we have seen, only one element having positive figure, while all others are having standard reduction potential negative. And in fact, the nature of the graph is like this. But you can see few exemptions. Somewhere in manganese there is an exemption. Somewhere cobalt nickel there is an exemption. Zinc is an exemption. So why the exemptionals are coming? Because, for example, zinc. Why zinc is becoming negative? Why zinc is turning negative? In fact, it is going like this. Zinc should have been somewhere over here with a positive figure, but zinc is having minus 0.76 volt. That is the reduction potential of zinc. Zinc coming very low value as a result of enthalpy of atomization. You see, what is deciding this standard reduction potential? Standard reduction potential decided by the three important thermodynamic parameters. You have metal solid, which is converted to M gas. And this value is enthalpy of atomization, which is an endothermic figure. Right? Now, this M gas is converted to M plus gas. That is first ionization enthalpy. Of course, it is endothermic in nature. And now this is converted to M2 plus in the gaseous state. That is second ionization enthalpy. Again, it is endothermic. And this is converted to M2 plus aqueous. that is hydration enthalpy, which is exothermic. I'm sure all of you agree to the feasibility of a reaction depends on the thermodynamic nature. Exothermic reactions are highly favorable. Endothermic reactions are less favorable. If it is endothermic, a low value is favorable. So, this is endothermic. The favorability decided by a low value. If it is a low value, the reaction is favorable. If it is a high value, reaction is unfavorable. Right? And this is exothermic data. A high exothermic data, the reaction is favorable. Or low value, the reaction is less favorable, like that. So, exothermic, endothermic nature of the thermodynamic nature of the reaction decide whole lot in the overall reaction. Right? And the overall reaction, you see, E naught value M2 plus bar M, it is highly negative. That means this is easily converted to this. This is easily converted to this. How it is decided? It is decided by a low enthalpy of atomization, a low first ionization enthalpy, second ionization enthalpy, and a relatively high hydration enthalpy. So this should be low, this should be low, this should be low, this should be high for a very high negative value of this. So a high negative value indicates this is low, this is low, this is low, and this is high. Right? In all these cases, when you examine, you can find the replication of the nature of this data is reflecting ultimately on the standard reduction potential. For example, zinc. Why the zinc is having a minus figure? In fact, it should be having a positive figure. Somewhere here the graph it goes like this. It's having a negative figure due to very low enthalpy of atomization. In the series, zinc is having low enthalpy of atomization. So that low enthalpy of atomization reflects in the data. So due to low value of this, the overall reaction is favored and it has got a negative value. Hope you get it. Right? On the other hand, for copper, why it is going to positive? Of course, it is having a reasonably good high enthalpy of atomization. Ionization enthalpy is very high. Second ionization enthalpy for copper is very high. This value for copper is very high. That is reflecting in its value positive. So whether a value coming more to negative side, whether a value going more to positive side, it is reflected by three thermodynamic data. Four thermodynamic data. One is enthalpy of atomization, first ionization enthalpy, second ionization enthalpy, and hydration enthalpy. That is the reason. Okay. So those data, when understood clearly, you can understand why the value is coming either plus or minus. You can see the second ionization enthalpy of copper is pretty high, and that is reflecting in the data. In fact, imagine this value, suppose it is minus 2121, suppose it is minus 2500. Suppose the hydration enthalpy of copper is bit more high. This value would have been negative. All are negative. Why copper alone is positive? Copper also would have negative. If it has got a compensating figure for this. This is high. Look at this value and look at this value. This is very high. Suppose this is compensated over here. Instead minus 2121. If it was minus 2600, just imagine. That value also would have been negative. Hope you understand. Because a high exothermic data favors the overall reaction. So overall reaction is governed by the individual steps. How the individual steps you have to look at, is it endothermic or exothermic? If it is endothermic, a low value is preferred. If it is exothermic, a high value is preferred. Atomization enthalpy endothermic. Ionization enthalpy endothermic. Hydration enthalpy exothermic. That is the point. Okay. So that is about the standard reduction potentials, whether it is M2 plus bar M or M3 plus bar M2. Next is a talk on halides. Next is a talk on halides. You need to have a meticulous look at this table and try to understand which all halides exist, which all halides does not exist. Like that, you should have a picture. You see that the various oxidation state from +6 to +1 to +6. Titanium giving 3 types of halides. There is a representation like this. X means or halogen. X means all halogen. That means TiX4 means TiF4, Cl4, Br4, I4, everything exists. TiX4. That means fluoride, chloride, bromide, iodide, everything exists. What about X1? X1 means fluorine to bromine except iodide. So what is that? VX41. VF4 exists. VBCl4 exists. VBr4 exists. VI4 does not exist. You have to get a picture clearly from the data, because there can be a question, direct question, which do exist, which do not exist. Okay. What about X dash dash? Only fluorine chlorine. Where is X dash dash? Fluorine chlorine. You see that? CuF2 exists. CuCl2 exists. CuBr2 does not exist. CuI2 does not exist. That is the point. What about X dash dash dash? X dash dash dash. All except fluorine. You see that? TiX2 dash dash dash. That means TiF2 does not exist. TiF2 does not exist. There is TiCl2, Br2, I2. So this kind of observation in various points you can see. The maximum titanium is +4. Maximum vanadium is +5. Maximum chromium is +6. Maximum manganese is +4. We know maximum oxidation state of manganese is +7. The +7 state of manganese is not given by halides. In fact, fluorides. Fluorides are well known for bringing to highest oxidation state due to high electronegativity, isn't it? But even fluorides are unable to bring manganese in the highest oxidation state. Please understand, the ability of fluorine to bring into the highest oxidation state may not be performed well. If it is so, manganese, we know +7 state, there should have been MF7 manganese in the +7 state. That is not observed. It is maximum observed is +4 state. So fluorine is not found to be performing well according to its basic character. Fluorine is helping other elements to bring to the highest oxidation state always. For example, BiF5. Bismuth never want +5 state, but BiF5 exists. BiF5 exists because of fluorine. Fluorine brings bismuth into the highest oxidation state, but the same fluorine unable to bring manganese in its first highest oxidation state. It's quite interesting. At the same time, it is performed by oxygen. Oxygen bringing manganese in the highest oxidation state. Quite interesting point. So the ability of transition metals to bring into the highest oxidation state is greater for oxygen than fluorine. Important point. Because oxygen is able to make multiple bond with the transition metals. Transition metals are well known for forming their multiple bonds. Here it is only single bond. Fluorine can make only single bond, while here you can make multiple bonds. It is forming multiple bond like this. Oxygen is able to make stable multiple bond with the transition metals, and that is the cause of superiority. Basically, the superior element for bringing an element to the highest oxidation state is no doubt fluorine, most electronegative element in the periodic table. But in this case, the ability to bring a metal atom in its highest oxidation state by fluorine exceeds compared to oxygen. Fluorine is less. Oxygen show better performance, bringing the metal atom in the highest oxidation state. And the cause of that superiority is nothing but the ability to form stable multiple bonds with the central metal atom. It's an important observation. This is also an important area where Cu-I2 does not exist. You see that? Cu2 halides are not except the iodide. What is the problem with iodide? This is a reasonably good oxidizing agent and this is a good reducing agent. Cu2 plus is a good oxidizing agent relatively. I minus is a good reducing agent. So there will be naturally a reaction. This is a good reducing agent, undergo oxidation. This is reduced to cuprous iodide. Cupric reduced to cuprous, iodide oxidized to iodine. That's why it does not exist. And this is another important point. Cu plus undergo disproportionation. Many copper-1 compounds are unstable in aqueous solution and undergo disproportionation. A very popular disproportionation example. Cu plus undergo disproportionation. Cu plus undergo disproportionation. It is oxidized to Cu2 plus and reduced to Cu. And see this area. The stability of Cu2 plus rather than Cu plus is due to much more negative hydration enthalpy of Cu2 plus than Cu, which more than compensate for the second ionization enthalpy of copper. You see, copper, it is D10S1. So losing one electron, it is copper plus. Losing one more electron, it is copper 2 plus. So copper plus is having D10 configuration. How it loses one more electron and Cu2 plus is stabilized? Because Cu2 plus got a greater hydration enthalpy compared to Cu plus. So when you compare Cu plus and Cu2 plus is more stabilized. Even though the second ionization enthalpy is greater, Cu2 plus is stabilized because of a compensating factor. What is the compensating factor? Hydration enthalpy of Cu2 plus is much more compared to that of Cu plus, and that compensate the higher second ionization enthalpy of copper. Another important point. You can find some important notes like this. Hardly we find iron. You see, beyond group 7, no higher oxidation state of iron above Fe2O3 are known. Iron basically shows two oxidation states, ferrous and ferric, +2, +3. But you see here, there is ferrates available. Ferrates is in the +6 oxidation state. Ferrates in the iron in the +6 oxidation, but not stable. Immediately it will decompose. Formed in alkaline media, but readily decomposes to Fe2O3 and O2. But there was questions connected to ferrite and its oxidation state related points. It is referred in the text. Usually what comes to our mind is iron +2, +3 only. But iron has a +6 state observed in ferrite. Make a note on to that. This is what the point I said. The ability of oxygen to stabilize the high oxidation state exceeds that of fluorine. Thus, highest manganese fluoride is MnF4, while highest oxide is Mn2O7. The ability of oxygen to form multiple bonds to metal explain its superiority. So, why oxygen is more superior compared to fluorine in bringing to the highest oxidation state? Due to ability to form stable multiple bonds. Okay. Have a look at the tabulated data of oxides. Various oxides are commended. Scandium, only one oxide. Titanium, you get 3 oxides. Vanadium, 4 oxides. Chromium, 4 oxides. Manganese, there are 5 oxides. And those starred ones will be mixed oxides. Starred ones will be mixed oxide. While you go to that side, only 1 or 2 oxides are shown. Chemical reactivity and E0 values. You know how the E0 value explain the chemical reactivity and its characters. If it is a high negative value, it can displace hydrogen from dilute mineral acids. It is strong metallic character. It's rather indeed it's a good reducing agent. The metals will be good reducing agent. While if it is a positive value, it is above hydrogen. It is unable to displace hydrogen from dilute acids. They will act as pretty better strong oxidizing agent, like that. All of us know the reactivity and standard reduction potential values. Now, magnetic property. Transition metals are well known for its magnetic behavior. Transition metals are well known for its magnetic character. Important magnetic character known to all. There are paramagnetic substances which contain unpaired electron. Paramagnetic substances weakly attracted in the magnetic field, paramagnetic. Weakly repelled in the magnetic field, diamagnetic. Paramagnetism due to unpaired electrons. Diamagnetism due to paired electrons. When all the electrons are paired, it is diamagnetic. When all the electrons are unpaired, it is paramagnetic. Or there are not all electrons unpaired. Presence of unpaired electrons, it is paramagnetic. Presence of all electrons paired, diamagnetic. What is the property para and dia? Dia means a weak force of repulsion in the magnetic field. What is para? A weak force of attraction in the magnetic field. Right? So many transition metals, or almost all transition metals, you can see they have unpaired electrons. At least the presence of one unpaired electron make the system paramagnetic. When the number of unpaired electrons are very high and overall the magnetic moment is performed very high, it is used for preparing permanent magnets and all. You know, it's called ferromagnetic. So paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. We are learning in another context, right? Fine. So transition metals are well known for their paramagnetic behavior. Paramagnetism arises from the presence of unpaired electrons. Each such electron having a magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of first transition series, the contribution of orbital angular momentum is effectively quenched and hence is of no significance. Experimental facts proves that for the first transition series, which one? 3D series, which one? Scandium to zinc. When you analyze the orbital, see, an electron is performed by two way of moment, orbital angular momentum and spin angular momentum. For 3D series, orbital angular momentum values found to be almost quenched, suppressed, and is of no significance. Only spin angular momentum is taken. It is determined by number of unpaired electrons calculated by spin only formula. This is called the spin only formula. Mu is equal to root of n into n plus 2. root of n into n plus 2, where n is the number of unpaired electrons and mu the magnetic moment in Bohr magneton. Bohr magneton. A single unpaired electron will have a Bohr magneton 1.73. Look at the magnetic moment, how it comes, and the number of unpaired electron, how it comes. Very simple to understand. Number of unpaired electron 1. What is the mu formula? Root of n into n plus 2. How it comes? Root of 1 into 1 plus 2. That is root 3. That is 1.73 Bohr magneton. Right? What about the number of unpaired electron 2? Number of unpaired electron 2, this is D1 and this is D2. It will be root of 2 into 2 plus 2. How much it is? Root 8. Root 8. Root 9 will be 3. Root 8 will be slightly less than 3. Maybe 2.8 or 2.9 range. Bohr magneton. You see D3 system, 3 unpaired electron, root of 3 into 3 plus 2, root 15, root 15, root 16 will be 4, root 15 will be slightly less than 4, maybe 3.9, 3.8. D4, that is 4 unpaired electron, it will be root of 4 into 4 plus 2, root of 4 into 4 plus 2, that will be root 24. Root 25 will be 5, root 24 will be slightly less than 5. So it is 4.9 Bohr magneton. Now D5 system, 5 unpaired electron and that is the maximum. It is 5 into 5 plus 2, that is root 35. Root 36 is 6, root 35 is 5.9. So 1 unpaired electron 1.7, 2 unpaired electron 2.8, 3 unpaired electron 3.9, 4 unpaired electron 4.9, 5 unpaired electron 5.9, D1, D2, D3, D4, D5, D6, 4 unpaired electron. See, D6, how many unpaired electron? Pairing starts. Exactly. 4 unpaired electrons, so it will come this side. D7, 3 unpaired electron, 3.8. D8, 2 unpaired electron, 2.8. D9, 1 unpaired electron, 1.7. Like that. Is that perfect? So that is the way the unpaired electron and the magnetic moment is coming. You see that the unpaired electron and magnetic moment is scandium to zinc. D0, it is no magnetic moment. Scandium 3 plus. D0, no unpaired electron, no magnetic. It is diamagnetic in nature. It is diamagnetic in nature. In fact, this is diamagnetic in nature. So scandium 3 plus, zinc 2 plus are diamagnetic in nature. What about the others? D1, D2, D3, D4, D5, D6, D7, 8, 9, 10 like that. Up to 9. It is number of unpaired electrons. D1, 1, 2, 3, 4, 5, 6. Not 6, sorry, 5. And then pairing starts. In D6, pairing starts. What is D6 pairing starts? It is 1, 2, D1, D2, D3, D4, D5, D6, 4 unpaired electron. D7, 3 unpaired electron. So up to 5, the number of unpaired electron increases and then decreases. So 1 unpaired electron, 1.7, 2, 2.8, 3, 3.8, 4, 4.9, 5, 5.9, like that. That is what the nature of magnetic moment. And that is an important property concerned to atomic and physical properties concerned to physiochemical properties concerned to the transition elements. You can do the in-text exercise questions based on which it's a very important point in the transition methods. And now the next is formation of colored ions. Formation of colored ions.